yours, Dr. Mohammed.
Thank you very much for this invitation, and it's my pleasure to give this talk. So as you presented, the talk will be about non-MgO materials as alternative barrier in MTJs, magnets and junctions for Spintronics applications. So I will go through many attempts, many results to substitute MgO. Okay, before that, I would like to acknowledge my collaborations in Japan, names GSPS Impact Project, especially Dr. Seiji Mitani and Hiroyuki Sugigawa. And also I want to present my current institute in Morocco, in University of Mohammed VI Polytechnic. We are a still young group, and we aim to do optomagneto effects with the 2D materials. And we are setting up a new lab with the cryogenic machines and laser and so on. So please, of course, if you're interested, please visit our website to know what's going on, what's our research. We have seminars also, if you are keen to give a talk about concerning all interesting parts about condensed physics, material physics, or even nuclear, you are welcome. Let's start the talk. So I will try to give a talk by introducing some aspect of MgO and also the alternatives. So this is my summary somehow. It's going to be like this. MgO suffers from several inconvenient parts, and by substituting MgO with alternative barriers, we can get new features, new options in terms of devices and also in material science. So like, for example, low resistance area, multi-bits, and larger PMA, perpendicular magnetic anisotropy, which is very crucial for industrial applications. And interestingly, the quantum well, I'm a guy who came from semiconductor physics. I did my master's in quantum well, then I did my PhD in Spintronics. So somehow I was keen to realize quantum well in Spintronics. So, and this cannot be realized by only MgO. So this is somehow the expectations, and let's go to the how we can reach this level. So the outline of my talk will be as follows. I will go through the magic combination. I like this nomenclature or this name because it's really iron MgO. Iron is a magic combination. We should admit this, but it suffers from some issues. I will present them. Then I will present later on the alternatives which are present in the literature. I just did a quick research this morning, just to update my knowledge about MTJs. Still, people are using MgO in skyrmine-based MTJs, in stochastic computing, in SOT, spin orbit torque MTJ, and so on. So we are still using. Sorry, we are still using MgO. It's really a magic combination, the iron MgO. So I will go through it. Maybe the audience is so wide, so we'll go through some explanations. So as we know, the magnetic resistance history is passed through many steps, starting from AMR, then GMR, and the Nobel Prize in 2007, then the TMR, expected first in alumina. Of course, it should start with something amorphous, done by Miyazaki and Modera in 1994-5. Then the famous prediction of spin filtering by William Butler. Then we have the realization in epitaxial MgO by Shinji in 2004, and after that, successive consecutive achievements done by Stuart Parkin, Hideo Ono group, concerning the perpendicular MTJs, the STT, and also on. In terms of performance, we started from, let's see, a magnetic resistance of 15% in 1995. Now we are in 600. Of course, I'm not talking here only about numbers, but also about the physics behind, which is the spin filtering. So by using MgO, let's say the iron MgO magic combination. This is a brief introduction to the spin-dependent tunneling. Without going through the details, the magnetic resistance can be expressed by this formula 2p1 p2 divided by 1 minus p1 t2. p1 and p2 is the spin polarization of two electrodes, and in case these two numbers are approaching 1, we might expect 100 a large number in MR, and which is the case of full polarized material or half metals Hustlers. Well, this is theoretically, but once we go to the reality, things are different. Let's go through a little bit about the MgO combination, magic combination. The good point is the lattice matching. You can find a good lattice match with iron. It's available, it's cheap, and it can be grow easily. Here I presented some aldehyde patterns showing the good quality of epitaxial growth. This has been done from 2004, easily in epitaxial. I will concentrate in this talk about epitaxial, also amorphous polycrystalline, polycrystalline fabrication of MTJs is also very important. But I will go through it also. So the first magic combination, the aspect of this magic combination is the lattice match. Easy, we can do it easily. Iron, we are limited somehow to iron. This is also an inconvenient, and the lattice match is 3%. This will implement some dislocation, misfits, and so on. Also, we are limited with the usage of the thickness around 1.3 nano. So below 1 nano, things start to become difficult. Also, we have the spin filtering. This is also one of the good aspects of this magic combination, the spin filtering, because of the iron. So without trying hard to find the Heusler or half metals, which almost very complicated materials, the iron itself is like it behaves like half metals. At Fermi level, the up spin, we have the bands of up spin, but the minority spin are absent around Fermi level. So when we go to the parallel one, we have delta 1 up, anti-parallel, the delta 1 down, minority are absent. This is one good thing. Sorry to summarize this, just for people who are not familiar with this. So I will go through this fast. In terms of alumina, aluminum oxide, alumina, all the orbitals, they tunnel in equally, and the bar itself, it's amorphous, polycrystalline, right? In opposite, we have a single crystalline MgO, for example. The delta 1 is beneficial, it's dominant, especially in the parallel. In addition to this, the decay coefficient of delta 1 in MgO is smaller than the other orbitals, the other bands, delta 5 and delta 2. And this is very important, which gives, if we go through the spin filtering effects predicted by Butler in 2001, in the parallel states, we have a dominant delta 1. Once we go to anti-parallel, we got the decay, and by this process, we expect high TMR. I will go through a little bit faster. So the combination gathers the small decay, the lattice mismatch, and also the textured MgO, which started from polycrystalline and which normally crystallized from the inside the MgO. Yeah, many researchers try to use other barriers, for example, gallium oxide, which is a spinel zinc oxide in terms of cubic. But the problem here, which is a good also aspect of MgO, is the surface energy. The surface energy compatible with iron. If you want to try other oxide, you need a seed layer. And this is also inconvenient for using the other ones. People just strive here to realize this barrier. Of course, we know as a reminder here, the objective is to reduce the RA. which is very important request. Is a request for ACT and MTJs. This is just the stack when you want to do the gamma, for example, gamma oxide. So you need a sealed layer. Just presented here in terms of crystals. Of course, someone might say, what about the semiconductors? There are many theoretical predictions about, for example, zinc selenide, gamma oxide. When you go to the first principle DFT calculations, things are smooth, delta 1's decay is less, but in practical, still we have defect, interface resonant state, which lowers the TMR. So MgO is still a good candidate. So what about the issues with MgO? I will go through them fast, a little bit fast. We have the misfit dislocations. In this paper, we did an extensive study about the surface, and we have here some cracks. Let's say cracks, dislocations. From the top, you see it like this. From a cross section, we have here misfit dislocation, which will diminish, for example, PMA, perpendicular magnetic anisotropy, and it will make the control of RA, resistor area, a little bit difficult. Yeah, this is another study about the dislocation. For example, for the phase image, this has been done by Nancy Group in France, and they try hard to overcome this. And the solution provided is to dope iron with vanadium. This is some way to lower the misfit dislocation and the lattice match. I remind you that the lattice match with iron and MgO is about 3 to 5%. And we are going to see, in case of spinels, this will be reduced to less than 1%. I like this paper. It was published by York University and Tohoku University as a collaboration, scientific report 2007. So they gathered the information from TEM, top view, cross view, they included in DFT, and they tried to approach the experimental TMR ratios obtained by experimentally. And they discovered that the shocking maybe result that actually the MgO should have a low band gap. So it's not the bulk value of 7.8 electron volt, but it's rather it has 3 electron volts. So we are, in my understanding, this is a new MgO with a lower band gap, and that's what really explains the saturation. If the saturation, yeah, I should apologize if I didn't bring this. Normally, the TMR with the thickness should increase because we are killing one-handed or diminishing, we are nullifying for very thick MgO in antiparallel the conductivity. But what happens in reality, the TMR saturates with the thickness, and this is one of the reasons. Yeah. In terms of thin MgO, for thinner ones, the performance becomes very bad, and the TMR is lower, and we start to have scattering and other effects. So we need to reduce this, especially for STT. I think we need the very low RA. This is handled in terms of industry by very sophisticated technologies. In my understanding, this can be overcome by using alternative barriers. Here I'm presenting the performance of almost, I refer to this brilliant report by Professor Hirohata from Tohoku University. So he gathered all the data from NGO-based MTZs and their performance from high temperature to low temperature, 330 to low temperature, and you can see the increase of the TMR at low temperature, of course. But for example, for the half metallics, normally we expect the performance to be high at room temperature, but this is not the case. So this is what it was explained by the the elemental diffusion, also mixture of elements that's constituting the Heusler's at interface plus the oxidation. So this is somehow the short point of with MgO. But still, MgO, I repeat, we are not in the phase to replace MgO yet, but it could be done in the future. This is the comparison with amorphous lattice match. So I'm going to present some our results concerning the lattice match barriers plus other ones. So Professor Hirata here, he just made a great comparison, great job. So all the defects, the short points concerning grain boundaries, interface defects, atomic disorder, and so on, they are minor somehow. In epitaxial MgO, iron MgO, they are present or dominant. Minor in amorphous growth, and lattice match, they are negligible. So let me summarize here to have the criteria for MgO alternative. It should possess a lattice matching with the ferromagnetic candidates. So here, if we change the barrier, we still have an area an area to choose the ferromagnet. The spin filtering effect to avoid the Heusler's, crystalline feasibility. Rarely we talk about this because this will concerns chemical aspects at the interface, and also we need to conserve the electronic magnetic properties at interface, which is not the case of zinc selenide and gallium arsenide. So I will just reach my parts. We could do this or solve some problems using these problems that faces MgO using spinels, hexagonal, and also recently to the barriers. I will start with the work I start from my PhD. Gradually, I was publishing a few papers. So we try to use. I was asking myself, why we don't do something not cubic, hexagonal? So we tried the magnesium zinc oxide. I will remind you here, the zinc oxide basically it's stable in the woodside hexagonal SCP. MgO is stable in the cubic one. So if you dope alloy, zinc with magnesium till 40–45%, you are still in the hexagonal. So this is the stack we try to optimize using cobalt platinum, even though it's still present some scattering, spin scattering due to the platinum. But we could realize a good texture of MTJs. Allow me to drink some water. So we could realize a TMR up to 100. This is very nice. Sorry if I couldn't bring the picture, but this result is under preparation, and we could at least overcome or get a spin polarization beyond the bulk one, for example, for cobalt, platinum and cobalt. Please visit our paper here to get more insights about these things. So if you include 100% in the Julier model, you will reach, plus the spin polarization of cobalt around 30–40%, will reach some high level, which means we are at the age of spin filtering with the woodside magnesium zinc oxide. There are some theoretical calculation. I think done by Professor Imamura of AIST, but he used a cubic one. So this is also a chance for people who are doing DFTs to try this material in DFT. So while doing my experiments, we start to find some hysteresis in the IV curves, and so that was an indication of ferroelectricity. This was in that time a few papers talk about the ferroelectricity in magnesium zinc oxide. So to implement ferroelectric barrier with MTJs, that will bring new features or options to realize, for example, multi-bit MTJs. So we did here something innovative. We took it from the electric field coiling, magnetic field coiling, when measuring the exchange biases and the FM, EFM interfaces, and we apply it to our barrier. Well, here we use electric field cooling to clear out the presence if you have a ferroelectric or not. We realize this by plus minus voltage, and we see there is a big difference by using some models that relay the tunnel electroresistance and the reversed electric polarization. We could estimate the amount of electric the reversed electric polarization. So this was published in recently. Hardly we could convince the review about ferroelectric in magnesium zinc oxide. Recently, few groups they are doing this. They are publishing this kind of similar results. Of course, there is many obstacles to overcome, which I will omit in this talk. So we also confirmed this by theoretical calculation, and as I mentioned before, the temperature dependence of reversed electric polarization, which shows here the Curie temperature of ferroelectricity. So we realized ferroelectric quartzite magnesium oxide thin film in MTJs, but this is one of the rare examples in MTJs. And later on, this is also very, very interesting. We use this ferroelectricity to create or to manage, to modulate the magnetic anisotropy of cobalt platinum. Without getting a lot of details, because of their ferroelectricity and the change of the charge at the interface, we could induce a large delta MAA of 2.6 erg per centimeter square, which is far away bigger than the case of MgO, of iron MgO. So we could, in short words, we could enhance the PMA performance in these interfaces. Here we move to the spinels. The spinels are well known, especially in in Heuslers, if I'm not wrong. But also there are also we have also many oxides like magnesium iron oxide, magnesium oxide, magnesium gallium oxide. And this is the structure of spinels. We have octahedral, tetrahedral structures. And here the important point is there are two configurations of spinels: disordered and unordered. So the ordered one, they are close to similar to the MgO, and this disordered one have like a double lattice parameter. Yeah. So according to theoretical expectation, the calculation similar to MgO, there is nothing new. The spin function exists. The decay of delta 1 is smaller than delta 5, delta 2. And the good point here is the lattice match with iron, for example, is 0.3. I want to bring to your attention, attract your attention, that if we modulate, for example, the composition of magnesium aluminum, a little bit magnesium rich, a little bit aluminum rich, we can get a lattice match with other ferromagnets, which is not the case of MgO. Also, we have many candidates. So in the beginning, we tried at NIMS to fabricate some good quality magnesium aluminum oxide, which is similar in terms of band gap, similar to MgO. Then we shift to magnesium gallium oxide. The band gap is 4.9. Then to the zinc aluminate, which has a lower band gap that I will show later. So by lowering the band gap, of course, we are expecting to lower the RA. After many optimization, of course, we need to have a target here with the oxygen rich. If you see here, sometimes this is also one of the problems in spinels is because we have 3 elements, so we need to care about the oxygen concentration. But even though, after many optimization, we could realize a high MR. I think now we are in the limit of 400 using magnesium aluminum oxide. This is one of the hysteresis, and you can see that the very clear interfaces, abrupt, and I will show you the degree of the silication later. Of course, the same thing happened with magnesium gallium oxide. We have a little bit lower one because of this effect, because we got an order one. The order one, we, in brief word, will bring some band folding, which brings new bands to contribute to the conductance, which at the end lower the MR. But I think this can be solved by some doping. So we proved that we have high performance spin oxide, and when we tackle the issue, for example, of low RA. This has been confirmed by using magnesium gallium oxide, and since it has a low band gap, we could realize using the same conditions of magnesium gallium oxide and magnesium gallium oxide a lower RA, which shows that we could realize low RA MTJs. This can be very beneficial for SCT, and especially we want to cross. We want to realize less than 5.1 ohm micrometer square. Sorry, this can be something beneficial, a good candidate. Also, when we are using the MTJs, we like to apply voltage. In many cases, for example, PMA and other applications. I don't know about skirmions, but this is the case. So you need to apply. As we know, once you apply the voltage, your TMR, because of many physical effects, will reduce. In the case of MgO, to reach the half of the maximum, you will do it just by 0.5 volt. In the case of magnesium aluminum oxide, this can be done easily. We can reach easily 1 volt. So this has been predicted and also confirmed. Sorry, not predicted, confirmed by a physical calculation by Professor Masuda of NIMS. Here is the FFT of the TM images that shows the diminution of this location once we use the spinners. I think I still have 5 minutes, yeah?
Okay. 8 minutes.
8 minutes, that's nice, thank you. So here we have some dislocation. You can see this yellow T marks. Then once with the magnesium aluminum oxide, we have almost three dislocations at the interfaces. It's not 100% perfect, but to be honest with you, the oxygen control, the oxygen density with MgO is much better than, or it's easy to control with the spinners. This is maybe the short point of the spinners. Here's the illustration of the lattice spacing. If you enlarge the scale, MgO is here, iron is here, and the spinel is here. Yeah. As a consequence, this is a study done by Dr. Sugawa at NIMS. We could increase the PMA performance. I will go through. Yes. Sorry. Meanwhile, by improving the interfaces, we start to see the physical features at the interfaces. This can be illustrated by the second derivative of the time conductive relatively to the voltage, and we see many features here. In my understanding, the last paper discussed this tunneling conductance. It was in 2009 or 10. So we need a lot of effort to understand these peaks, from where it comes. It is magnon. It's really interface magnon. It is the barrier. But at the end, these peaks represent the quality of the interfaces. In our case, we could get some good unsharp peaks. Yes. I will present here. Then, so we have very flat lattice match iron magnesium aluminum oxide. So we expect to have a coherent tunneling through this interface. And this, in reality, what has been confirmed by many groups. We will start with the chronological achievement. This is a collaboration between the Chinese Academics of Science and Nancy Group, and they realized this is the first realization of the metallic quantum well. This is very important. If you heard about quantum wells, it's almost done in semiconductors. It's realized in semiconductors. But nowadays, because of this, because only this interface, the iron magnesium oxide, we can achieve this. This paper changed the thickness, they did the calculation, and they confirmed this is a quantum well. If I didn't mess up here, it's the parallel. Yeah, it's the parallel configuration. Here you see the peaks, the oscillation, especially in the minus bias, and they confirm by a calculation that if you induce if you implement the MgO, the oscillations are very smaller, and with the spinel, the oscillations are big, are relevant. So this is an evidence of quantum well resonance state, and this has been realized with the quantum well up to 12 nanometers, which is not, in my understanding, in terms of semiconductors, this is even difficult to realize because because we need a coherency for the electron phase. Our group also, we did also the similar thing, but we concentrated more on the TAMR, the tunneling anisotropic magnitude resistance. We changed, we realized here a quantum well. Here is different quantum well. We didn't use the barriers, the physical barriers, but we used the delta one, because so we have here a delta one, let's see, type quantum well. So in the parallel state, since for the chromium, we don't have a delta one configuration. So here, delta one down spin. So we have this quantum well in terms of delta one, and by changing the magnetization, we could shift, or we could shift the quantum well levels by around 50, if I didn't miss up, 50 milli-electron volt. So this is very important. We can talk about the magnetic field. It's like we gate the quantum well with magnetic field. So this is also one of the consequences of the good interface at iron magnesium aluminate. Several also two papers talk about the same thing. Here, the double quantum well, which enhance more the coherency and the resonant tunneling through the iron. Of course, here we concentrate the more all this studies use iron because as obviously because of the small lattice match. So this is by using some let's see interfacial some insertion. We can see here, for example, this is another paper using an insertion of cobalt. The conductance reduces a little bit, and here just they talk more or less about the effect of insertions. But the main idea is this iron magnesium aluminum oxide give you an option to realize coherent tunneling devices. I will present another candidate, which is a spinning zinc aluminate. So similarly, the good thing about this material, it has a very low band gap, 3.8. We did a lot of material optimization in order to realize high quality. Of course, here we needed, as you can see here, we need some insertion, but at the end, we could realize more than 100 TMR at room temperature, and this was the preliminary result. This needs, of course, some optimization and some enhancement to enhance the quality, and why not get rid of the insertion. This research is under preparation for submission. Lastly, I think I still have 1 or 2 minutes. We explored the thickness dependence of TMR, and we saw, surprisingly, we saw some oscillations. This is also one of the puzzles in MTJs, if you didn't heard about it. If you read the paper of Professor Shinji-Yuasa in 2004, you saw the similar oscillations. Normally, as I said before, the TMR should increase, it will increase linearly or somehow linearly once we increase the thickness, but here we saw oscillations. There is a key paper to understand what happens here. I will not get much in details, but if there is a question about it, I will answer about it. But there are 2 things here. Up to now, there are 2 solutions or 2 proposals. One says we have, this is a paper but not done by a group of Nancy group. So there is because of we have the resonant states, which is unavoidable. We have a mixture of delta 5 minority and delta 1 majority, which give us more channels that combines with the delta 1 and delta 5 up on the other side and give us more channels that contributes to this fact. Recently, a paper at arXiv suggests that there is a superposition of majority spin delta 1 and minority spin delta 2. So we are talking about almost the same thing. I think they got the idea from here, and they do some analytical calculation and they extract the oscillation. I hope this paper will be approved for review during the review, and we confirm the solution of the puzzle. I will come back to the same slide I start with. By integrating novel barrier within MTJs, I'm quite sure we can go for interdisciplinary application, novel paradigm of MTJs. And as I mentioned, the realization of metallic quantum with the current resultant is also of big interest. Thank you for your interest.
Thank you, Dr. Belmoubarik, for your interesting presentations and on-time presentation. Thank you for this. I would like to ask the audience if you have any questions. Just feel free to raise your hand or write any questions in chat.
Well, that's clear.
Yeah, I guess so. Yeah,
You have a question, please?
Please.
Actually, thank you for your interesting presentation. Very useful, actually.
Thank you.
Actually, I can see in your slides, sometimes you grow in magnesium aluminum oxide with phase center cubic structure and sometimes base center cubic. So what most parameter controlling the texture transformation from this one to this one?
Again, I couldn't get you.
Yeah,
sometimes
actually,
when I grow,
yes, sometimes you grow magnesium aluminum oxide, maybe on top of cobalt iron boron or on top of iron, and then sometimes it's texture with base center cubic 100, and then other times it's like texture phase center cubic as it is. So what is the most parameter controlling this texture to grow in this way or in this way?
I think if I understand well your question, the spin in magnesium aluminum oxide is always cubic, okay? So it's a spin in cubic, okay? So I don't think it's going to be FCC, okay? So did I understand your question? Yeah, yes or not? Okay. So let me finish. Let me just give you a key point here. It's always going to be cubic, spinel cubic. What's going to happen based on the oxygen deficiency or how to say it, how much oxygen we have in the environment, either it's going to be ordered spinel or disordered. So this is what's going to happen. And this is really the hard part of spinel, which doesn't exist in MgO. So if there is, let me summarize a little bit. If we have ordered one, okay, normally we want to have this order one to avoid the band folding. Please, the band folding. So we want to have this ordered one, just to have the spinel lattices in less bands, okay. But once we have this disturbance of or the sites of magnesium are not really well defined, we have this which is close to MgO. So normally we want to use the disordered one. Okay.
Okay. Thank you.
Yeah. Yeah, I didn't mention the paper here. I think there is a PRB of Professor Segega 2010. So he talked about this. Yeah, Segega 2010. He talked about this band folding. Actually, this is one of the things that should be controlled in spinels. Yeah.
Thank you for your clarification, Dr. Mohammed. Of course, if you need extra information, lastly, you can still reach out to Dr. Mohammed either by email or in the gather town if you have like extra questions. Do we have like some other questions from the audience? Don't be shy. If you have any questions, you can just feel free to ask them, even if it's like basic questions.
Yeah.
I'm be glad to respond to everything.
I have short question, if possible. So you mentioned actually that there is like in your system you have oxide metal interfaces, right? And it could be like that we have some oxidation or reduction at the interface. Is this affect the TMR properties?
Yes, yes, it will affect. Basically, it will reduce because normally what brings the performance is a well-established spin polarization at the interface. So if you have an oxidation of the top surface, the spin polarization of that electrode will diminish. And this was handled normally even in MgO by the insertion of some metals like magnesium, or for example, in this case, magnesium aluminum. Okay, so this will in MTJs will reduce the interfacial spin polarization, which affects the TMR. If you are doing PMA, you will get out of control of the things. So it's like you have another oxide, which in other terms, you have another oxide, which is not spin filtering. Okay. Did I answer your question?
Thank you a lot.
Okay.
Thank you a lot for your nice talk.
Yeah.
Thank you.
Thank you.
I have a question for myself, like which is just maybe not very technical, but I saw like OCP company. So are you from AP working in collaboration with OCP? Because I know
we are in our university. Yeah, our funding comes almost from OCP. Yes.
Okay,
this is in short. So we are financed by OCP. Yes. This is written in the homepage of the M6P. Of course, we need to get funds from other agents, but since OCP has in this project of doing education and pushing research in Morocco, this was the idea of establishing UM6P.
Okay.
Please visit our website to get more insights. I repeat, if one of you wants to do some seminars, to deliver talk, in some physics-related thema, please just contact us, and we'll be happy to welcome you in our weekly seminar.
Yeah, I guess you can get like the information of Dr. Mohamed Belmoubarik from ATC website, from the conference website, and you can go check from invited speaker, and you can easily reach out to Dr. Mohamed Belmoubarik by email.
Yeah.
Okay, so we're almost done for this plenary talk, except if there are some other questions, you can still ask them. If there are no more questions, we can go to the oral presentations. So thank you again, Dr. Mohammed, for your presentation and for accepting this plenary talk. So we will now to the